Hi, in this video we'll be looking at the calculations required to determine the pH over a range of volumes in a titration curve. I'm showing a classical titration curve. In this case I'm showing a strong acid, NaOH, titrating a weak acid, which I have identified just as HA for this example. So here we have kind of four distinct regions of a pH curve, of a pH titration curve. The first is the initial pH. And then we have an area after the initial pH of what we call the buffering region. And we're going to calculate that just as if it was a buffer using the Henderson-Hasselbalch equation, until we reach the equivalence point. At the equivalence point, the moles of acid equals the moles of base. After the equivalence point at part 3, we have excess base in solution, and you're going to see the pH rise pretty quickly. These calculations in these regions are a subset of calculations that we have already done in this course, just a slight different application. So nothing we're going to talk about today is really new in terms of calculations, but we're just going to kind of look how we apply it in solving titration curves. So first we're going to look at the initial pH. So for initial pH, we are going to calculate the pH of a 50 ml solution of 0.25 molar weak acid. And I'm providing a Ka value of 6.5 times 10 to the minus 5th. So we can solve this using our ice table technique. Initial change equilibrium. We have initially 0.25 molar acetic acid. We haven't added any base at this point, so we're just looking at a straight equilibrium reaction. So acid plus water gives me weak base plus hydronium ions, so nothing here at the beginning. My change is going to be minus X for my weak acid, plus X for my conjugate base, and plus X for my hydronium ion. We look at the equilibrium. 0.25 minus X plus X plus X, and we know from our Ka expression that this solves into Ka equals X squared over HA, with the assumption that X is small, and that equals 6.5 times 10 to the minus 5th. When we solve this, we get X equals 4.03 times 10 to the minus 3 molar. To get pH equals negative log of our X, and the pH is 2.39. So I can mark that on my graph here as 2.39 at 0 mils, we'll just put the unit down here, of NaOH. The next point that we're going to look at is in the buffering region. In order to determine what the buffering region is, so here, we really have to figure out where the equivalence point is. So we're first going to have to study the point where the moles of acid equals the moles of base. So we can look at, again, we're looking at a different reaction now. We're looking at neutralization, so our weak acid plus our strong base. We have a double replacement. Sorry. We have a double replacement reaction. Here, I left off our Na plus ion. It's a spectator ion in this solution. So here we can look at our initial condition. Moles of acid equal moles of base. I have 0.25 molar acid. I have 50 mils. My moles of base, I have 0.1 molar sodium hydroxide. I said that in the initial problem statement. And the question is, how many mils of sodium hydroxide do I need to add here? Everything is 1-to-1, so that makes this a very simple calculation. So I have 12.5 millimolar. When I multiply my moles times my mils, so 1 mole, I have to have 12.5 millimolar of my base at the equivalence point. And so when I go to solve this, I can take 12.5 millimolar divided by my molarity of the base, and that gives me 125 milliliters. So I'm going to write that here. So once I've added 125 milliliters of base, I have reached the equivalence point of this reaction. So now I want to know kind of what happens. How do I calculate the pH now in this region 2 when I have greater than 0 but less than 125 mils in my solution? So we're going to look at this same reaction, this same neutralization reaction. And I still have 0.25 molar. I'm going to call this before reaction again, of acid. I have 50 mils. And now I have 0.10 molar, and then 50 mils of NaOH as well. And this now is a limiting reactant problem, and the NaOH is going to be my limiting reactant. So I still have my 12.5 millimolar acetic acid, or whatever acid I'm dealing with, my weak acid, 5.0 millimolar of my strong base. Initially, I don't have any of my ion. And then I'm going to do my change. And so because this is limiting, it's going to be only minus 5.0. And then now I'm going to produce 5.0 of my my conjugate base. So after this reaction occurs, I have 7.5 millimolar of my acid, and I have 5.0 millimolar of my conjugate base. And this should, and no strong acid. And so when I have this situation, it should look like a buffer. So if I have, weak acid and its conjugate base in solution, I have a buffer. So I can convert this into concentrations. And at this point, you have to remember to use your total volumes. So if I want my concentration of HA, going to equal 7.5 millimole divided by my total volume is 100 mils because I've added 50 mils of my NaOH and I had 50 mils of my acid to begin with. So the concentration of that is going to be 0.075 molar. I can do a similar calculation to calculate my concentration of base, and I get that to be 0.050 molar. I'm going to clear some space over here under my reaction. The easiest way to solve this problem is going to be to use Henderson-Hasselbalch at this point. So we use Henderson-Hasselbalch, which is the pH equals the pKa plus the log of base over the log of acid. The pKa is equal to 4.187. That's from the Ka, taking the negative log of the Ka value, plus the log of 0.050 molar over 0.075 molar. And that equals 4.01. So any point along region 2 can be solved using that technique. I went ahead and marked our point now, 4.01, at our 50 mils. Another point I want to point out in this region is known as the half equivalence point. The half equivalence point, I'll just label that 1/2 VE. In this particular case, it's 1/2 of 125 mL, so 62.5 mils. At this point, once you solve the neutralization problem, you find that the concentration of HA is going to equal the concentration of A minus. And when you look at the Henderson-Hasselbalch equation, plus the log of A minus over HA. If these two concentrations are equal, we have 1 here, and then the log of 1 is 0. And so the pH is going to equal the pKa at this point. So the pH equals pKa, which equals 4.187. And that's at the half equivalence point. Be careful not to take the pH at the equivalence point and just divide by 2. It's not the pH, it's the volume that divides by 2 to get your half equivalence point. So with that, that's kind of how we will deal with the buffering region. The next region I want to look at is at the equivalence point, which we previously calculated was at 125 mils of our 0.1 molar NaOH. And how we solve problems at the equivalence point, again, we can look at our equation, HA plus NaOH gives me A minus plus Na plus, I'll leave that in there, plus water. Looking at our before reaction, molar, 50 mils, 0.10 molar, and now we know 125 mils. If the problem just directly asked for the pH at the equivalence point, you would have to go through the exercise to figure out the volume at the equivalence point first, like we did on the previous slide. Our change. So this is 12.5 millimoles. No limiting reactant here. So my change minus 12.5 millimole. And then on my product side, plus 12.5 millimole for our, sorry that got a little bit off, but for our weak base. So I have 0 millimole of HA, 0 millimole of NaOH, and then I have all weak base in solution. Divide by your total volume to get back to molarity. 175, sorry. 175 mils. And so that gives me my concentration is 0.07742 molar. Sorry, 0.0714 molar. And that's the concentration of my weak base. So because I no longer have any weak acid present, I am no longer buffering. We're going to solve this by using our KB expression now. So if I have a weak base, my reaction is now A minus plus H2O is in equilibrium with weak acid plus OH minus. Again, looking at a ice table, we can solve it, or we can remember that basically the solution to this is KB is going to equal X squared over my A minus concentration. And remember, KB is going to be equal to KW divided by KA. And because these calculations tend to be long, you do want to kind of just get used to the patterns for how these problems, these ice tables, solve out. And that will just speed up. If you kind of want to know where I came from this, I suggest you go back and watch the pH of a weak base video that's also on the YouTube. So when I go to solve this, this is equal to 1.53 times 10 to the minus 10. X equals 3.315 times 10 to the minus 6 molar. And that equals my hydroxide concentration, very important, which leads to a POH equal to 5.47, or a pH of 14 minus 5.47 of 8.52. So it's important to note that the pH at the equivalence point for this type of titration is greater than 7. So if I had a strong base, strong acid titration, I would have a pH of 7. here, because my neutralization product is a weak base in and of itself, at my equivalence point I'm going to have a slightly basic pH. In this case, it calculates to be 8.52. Where's that wrong? 8.52 here. Alright, so we're almost done. The last region is where we have excess base. So we are now looking at the region that is past our equivalence point. And we have excess strong base in solution. So this is going to be how you'll do any calculation in this region. Still looking at the same neutralization reaction. And I still have my 0.25, my 50 mils, 0.5 millimolar. And here I have 0.10 molar. And now I have 135 mils of NaOH, because note I'm greater than the equivalence point, which was at 125 mils. So I have 13.5 millimole of NaOH. So note now with this problem that my acid is now the limiting reactant. So when I go to do my change, I'm still going to make my weak base product. My after reaction, I have 0 moles of weak acid. I have 1.0 millimole of my weak base, and I have 12.5 millimoles of my weak base. So what happens here is, and I can convert this back to concentration, I have 185 mils total. So I have 5.4 times 10 to the minus 3 molar strong base, and I have 6.75 times 10 to the minus 2 molar of my weak base. Because this is a strong base, the NaOH, as long as you are little bit away from the equivalence point, the strong base is going to dominate the pH versus the weak base in solution. So when I determine my pH, the OH concentration is strictly from the excess NaOH that's contributing to the pH. It doesn't mean the weak base is not there and putting some OHs in solution. It's just the strong base is so much more dominant that we can neglect what's coming in from the weak base. So I can take the negative log of that and get my POH equals 2.27, and my pH then is 11.73. So that concludes all the major regions of the titration curve. In summary, for a weak acid strong base titration, these are the calculations that we're looking at. We're doing our Ka expression for the initial pH. For the buffering region, we're going to solve our neutralization reaction and then put it into our Henderson-Hasselbalch. For our equivalence point, region 3, we're going to solve our neutralization and then put it into our Kb expression. And then lastly, in the excess OH region, region 4. We're going to solve our neutralization and then determine how much OH is in excess from our strong base and determine pH from that. And that will allow you to get any point along a titration curve. So, thank you for listening, and I hope this helped you guys, and I'll talk to you guys soon.